In this video, we're going to learn about the complementary angle theorem and how to use it. So what is the complementary angle theorem? Well, I drew a right triangle, and the one thing I want to point out is besides the right angle, the other two angles would be the other 90 degrees of the 180 degrees of that triangle, making them complementary angles. So if I were to take the sine of B, which would be opposite over hypotenuse, which would be B over C. This would be equal to another trig function using the A angle. If I use the A angle, B over C would be adjacent over hypotenuse, which we know as cosine. So we see here that the sine of B is equal to the cosine of A. And if I did the cosine of B, which would be adjacent over hypotenuse, A over C, then I would get, using angle A again, opposite over hypotenuse, which is sine. So you'll see here sine and cosine, cosine, sine. These are known as cofunctions. So it would definitely be very easy to say that if tangent of B should be equal to cotangent of A, and then cotangent of B should be equal to tangent of A, using those complementary angles. And let's just test out this theory. So tangent of B would be opposite over adjacent, so B over A, and then cotangent of B would be adjacent over cotangent of A would be adjacent over opposite, which would be B over A as well. And now check out with cotangent of B, which I know as adjacent over opposite, so A over B. And then tangent of A would be opposite over adjacent, which would be A over B as well. So it's a really nice fact that we can use to simplify these trig expressions in different ways. So cosecant of B should be equal to secant of A, and then secant of B should be equal to cosecant of A. Again, B and A have to be complementary angles for this to work. And just to check, cosecant of B would be hypotenuse over opposite, so C over B. And secant of A would be hypotenuse over adjacent, which is also C over B. And then secant of B would be hypotenuse over adjacent, so C over A. And then cosecant of A would be hypotenuse over opposite, which is also C over A. So the statement we can make is that cofunctions of complementary angles are equal. What I'm boxing in is the complementary angle theorem. So let me show you how this is used. So sine of 62 degrees is equal to another expression. It's also equal to the cosine of the complement of 62 degrees, which we usually find by just taking it away from 90 degrees. So in this case, 90 minus 62 should give me 28, 28. So sine of 62 degrees is equal to cosine of 28 degrees. If I had this in radian measure, then I would say that tangent of pi over 12 is equal to cotangent of pi over 2, which is another way to say 90 degrees, minus pi over 12 to find that complementary angle to pi over 12, making cotangent of 6 pi over 12 minus pi over 12 cotangent of 5 pi over 12. So I can say that tangent of pi over 12 is equal to cotangent of 5 pi over 12. And let's say that a trig function is being squared. Well, it still works out the same. I'll just say that sine squared of 50 degrees is equal to cosine squared of the complement of 50 degrees, which would be cosine squared of 40. Now let me show this in practice when you have expressions with different angles, and if you recognize that the angles you're looking at are complements of each other. So first, 10 and 80 are complements. So one thing I can do here is change one from cosine to sine or sine to cosine. But in this case, I'll change my cosine to a sine by saying cosine of 10 degrees is equal to the sine of 10 degrees is complement. 90 minus 10 degrees is 80. So I end up getting sine of 80 degrees over the sine of 80 degrees, which simplifies to 1 because they cancel out. But let's look at 1 minus cosine squared of 20 degrees minus cosine squared of 70 degrees. 20 and 70 are complementary angles. So what I could say is that this is equal to 1 minus sine squared of the complement of 20 degrees. So 90 degrees minus 20 degrees. You may be wondering if they are both cosines, why am I changing it to sine? Well, they are squared, so I want the angles to actually match for me to possibly be able to use a Pythagorean identity. Because doing so, I get 1 minus sine squared of 70 degrees minus cosine squared of 70 degrees. And you may also be thinking right here, well, those are both negative. I know the Pythagorean identity, which I'll write down, is sine squared of theta plus cosine squared of theta, and that gives me 1. Well, if I were to factor a negative out of those two terms, I'll get 1 minus parentheses sine squared of 70 degrees plus cosine squared of 70 degrees, which gives me 1, making this 1 minus 1, which is 0. Now lastly, I have several trig functions. But again, I do recognize that 35 and 55, when added together, give me 90 degrees. So these are complementary angles. So what I can do is use the complementary angle theorem to change my cosecant into a secant, to use 35 degrees, and my cotangent into a tangent so I can use that 35 degrees. So again, cosecant, its cofunction is secant, so secant of 35 degrees times secant of 90 degrees minus 55 degrees, its complement, minus tangent of 35 degrees times tangent of 90 degrees minus 55 degrees, the cofunction of cotangent. Simplifying this, I get secant of 35 degrees times secant of 35 degrees minus tangent of 35 degrees times tangent of 35 degrees. Now all the angles are matching, and I also see that I'm getting the same thing twice. So I can rewrite this as secant squared of 35 degrees minus tangent squared of 35 degrees. Which, what does this equal? Well, if I look back at my Pythagorean identity, I could divide everything by, let's say, cosine. So I get sine over cosine, which would be tangent squared, plus 1 equals 1 over cosine, which is secant squared. And by subtracting tangent squared from both sides, I see that 1 is equal to secant squared of theta minus tangent squared of theta. So secant squared of 35 degrees minus tangent squared of 35 degrees should equal 1. And that is how you use the complementary angle theorem.